Hi everyone, today we're going to continue studying linear transformations and understanding the different subspaces associated with them. So to begin, T is going to be our linear transformation. It is going from n-dimensional real space to m-dimensional real space. So Rn to Rm. We're going to be primarily utilizing the matrix representation of our linear transformations, in this case given by A. So we take our vectors in Rn, we have them be column vectors, and so we have our matrix transformation A times our column vector X, which would then give us a vector in Rm. So to begin, we have the kernel of our linear transformation, so our kernel of A. This is denoted by ker, K-E-R of A. This is the set of all vectors in Rn such that our matrix A times that vector X is equal to the zero vector living in m-dimensional real space. Another way to denote the kernel is the null space of A, so written as null of A. And as a reminder, this is a subspace of Rn. We're taking a collection of vectors within Rn, and they have the property of a vector space. 0 gets sent to 0. If you add two vectors which themselves get sent to 0, their sum will get sent to 0, and the scalar multiple of any vector going to 0 will itself also go to 0. So this is a subspace of Rn. The second set is going to be the image of A. So the image of A is going to be the set of all the matrix A times the vector X, where X is one of our inputs in Rn, and this is a subset of Rm. And indeed, it is a subspace of Rm. We have that it lives in Rm because we're looking at where do matrices from our inputs go in their outputs. So we're only looking at the outputs, and the holds the same properties of being a subspace due to how linear transformations work. We call the dimension of the kernel of our matrix A the nullity of A, and we call the dimension of the image of A the rank of A. Now that we've gone over the image and the kernel of a linear transformation, we're going to go over what it means for linear transformation to be one-to-one and what it means for it to be onto. I put in parentheses here the words injective and surjective. Being one-to-one is equivalent to being injective, and being onto is equivalent to being surjective. These are different words. In other areas, they have more distinct meanings to them, but for our situation in linear algebra, we can use these two words interchangeably. So if I ever say injective, know that I mean one-to-one. If I ever find myself saying surjective, know that I mean onto. So we have our linear transformation given in matrix form by A going from Rn to Rm. We'll say that A is onto if the image of A is equal to Rm. And we say that A is one-to-one if our matrix A times a vector X equaling our matrix A times a vector Y implies that X has to equal to Y. So what do these two concepts mean? I'm using a nonlinear case. I'm using polynomials here as an example. For being onto, the idea is our function hits everything. So we have functions are defined by inputs and outputs. The idea of being onto is that we have our space of inputs wherever our inputs live, in this case Rn. We have our space of outputs wherever our outputs live, in this case Rm. And being onto means that whatever space we're talking about for the output of our function, with looking at all of the possible inputs and seeing where they all get outputted to, we hit every potential output in the world that we map to. So this function is an x cubed, it's x cubed plus x squared or so. But you can imagine this polynomial here, every single y value is eventually hit by some x value. From all negative infinity to positive infinity, there will always be some input that will get you whatever output you want. So another way of saying is that every y, or every output, has at least one corresponding input, at least one corresponding x. The idea of one-to-one is to say that every output has only one input. So this is to say there's never any overlap of your outputs and your inputs. So as an example, this function here is arctangent. Arctangent only lives between minus pi over 2 and pi over 2. So it has a period of pi. So you don't hit every single possible y value, but every y value has only one corresponding x value that reaches that y value. In terms of why are these concepts important, if your function is onto, then that gives you information about what you can do to your output space. So whenever you're dealing with inputs and outputs of your function, if your function is onto, that means that wherever you look at in your output space, you can get there somehow from some input within your input space. Alternatively, for the function to be one-to-one, what this says is that if you had an output to begin with, there was no ambiguity of where was the corresponding input. There could only ever have been one input to that particular output, so your function had a kind of uniqueness in that sense. Now that we have the definition of what it means for a matrix transformation to be one-to-one, we're going to go over its relationship with the kernel of our matrix. So if we have our matrix A as a linear map from Rn to Rm, it'll be one-to-one if and only if the kernel of that matrix is the zero vector. What the phrasing if and only if, abbreviated here as IFF, what this means is that being one-to-one implies that the kernel is going to be zero, and if you have the kernel is zero, then that implies the function is one-to-one. Why is this true? Well, if we start off saying our matrix A is one-to-one, this is a one-to-one linear transformation. If I take any vector within the kernel, I'll have, by definition of what it means for a vector to be in the kernel, that our matrix times our vector v will equal to the zero vector in Rm. But we also know, just by the property that multiplying by zero always gets us to zero, our matrix A times the zero vector equals the zero vector in the output space. So because this function is one-to-one, two inputs have the same output, so the two inputs have to be the same. V has to equal to zero. Every vector in the kernel equals to zero, so the kernel can only be made up of the zero vector. On the other hand, if you say the kernel only has the zero vector, if I start testing the property for a function to be one-to-one, so I look at the output of the function for two inputs, you want to get to the point that you can say those two outputs, if they are the same, the inputs had to have been the same. So I'm saying that the output via x and the output via y are the same output. I subtract ay from both sides, so I get ax minus ay equals the zero vector. From here, I can use the distributive property of matrix multiplication. Vectors are just considered n by 1 matrices, so we have matrix multiplication working behind the scenes here. I can quote-unquote factor out a from this distribution, so I have a times x minus y equals to 0. Now I have the matrix A times something equals 0, which is to say that this input here is in the kernel of our matrix. So x minus y is in the kernel of our matrix. But going back, we said the kernel of the matrix can only be the zero vector. So for this matrix, this vector subtraction, x minus y, to be within the kernel, we have to have that x minus y is equal to 0. In other words, x has to equal to y. So this gives us how a function being a one-to-one can be checked by seeing what the dimension of the kernel is, or what vectors are within the kernel of our linear transformation. As a quick example, the identity transformation from a vector space to itself, so from Rn to Rn, this is both one-to-one and onto. We have that it is onto, it's hitting every vector in our output, because it's saying the output for a given input is just the input itself, and the two spaces are the same. So if I have a desired output vector x, its input to get there would just be x itself. Similarly, it's one-to-one because the matrix representation of this vector of this transformation here is just the identity matrix. If I have the identity matrix times a vector, that gets me the vector itself. So I would have up here the vector times the vector, so I would get that it's the vector equals the vector itself, so I would get the equality on both sides. We have more ways to check if a matrix transformation is one-to-one or onto. Here, A is our matrix, it is m by n, so it is going from Rn into Rm. We have that A is onto if and only if the rank of A, which is the dimension of the image of A, is equal to m, this m over here. And we have that A is one-to-one if and only if the rank of A is equal to n being the dimension of the input space. The easier of these two statements to show is the first one. if the dimension of the image is m, that means that the image, the dimension of that subspace is m-dimensional. So it's an m-dimensional space, an m-dimensional space. It has to be the entire space. Alternatively, if the dimension of our image is, if we have our image is, our function is onto, we have that we're hitting everything in the output space. So we're hitting the entire output. The output has dimension m, so we're going to have in our output dimension m. So the first statement is not too complicated to prove. The second requires appealing back to matrix transformations being another representation of homogeneous systems of linear equations. So if I have the rank of A is equal to n, this looks like I have my m by n matrix, and instead of row echelon form, I'm going to think of it as in reduced row echelon form. So the rank of the matrix is computed once you have row echelon form, but I'll take the step further and say we have reduced row echelon form. I have my rank of n, which means I look at my columns. Every single column has a leading 1. So I have here 1 on the 1-1 position, a 1 on the 2-2 position, a 1 on the 3-3 position, all the way into the n position. And there might be more positions underneath there for more rows, but at the very least I'm focusing on this n by n submatrix, you can think of it as. So now I think of what matrices multiplied by this coefficient matrix gets me to the all zero matrix. So we've done linear transformations on the rows, so the matrix transformation is maintained. So if I do the first dot product, I have this column, dot product with dot product of this first row. I pick out the first entry over here because it's this vector times that vector. So I get x1 has to equal 0. Over here I'll have x2 needs to equal 0. x3 needs to equal 0. All the way to xn needs to equal 0. And because this will be in reduced row echelon form, any other possible entries down here will be all zeros, so there's nothing else that can happen there. Which is to say that the only way our matrix can multiply to 0 is if this is the all zero matrix, which by what we have just shown is the equivalent to saying the kernel being just the 0 vector is equivalent to saying our function is 1 to 1. And then you can go backwards from there. If it's 1 to 1, I have my input gives me the output of all zeros, so the only way that I could ever get that is if I have just a 0 vector. And that comes from just looking at the rank of our matrix. After we look at the rank of our matrix, we can have a better understanding of this. We can talk about the rank nullity theorem. The rank nullity theorem gives us a correlation between the rank of a matrix and the dimension of the kernel of that matrix. So the rank nullity theorem says n, the dimension of our input space, is equal to the rank of A, so the dimension of our output, plus the nullity of A, the dimension of the kernel of our function. So the reason this theorem is so important is that it gives you, once you are able to compute the dimension of either the image or the kernel, you can immediately compute the dimension of the other. Because n is a constant. It is just what is the dimension of the input. If I compute the dimension of my output, then I can just find the dimension of the kernel by subtracting both sides by the rank. Or alternatively, if I first find the dimension of the kernel, I can subtract both sides by that number to get the dimension of the image. So this gives you a faster way to compute both pieces of information, and this shows the relationship between the two of them.